Welcome to information on section 7.2. This is a section about volume again, but building the volume through cross-sectional areas. And I've got the next page. You should have the note sheet that looks similar to this. And you'll see here that there are shapes that are stuck along the base region. There's our base, and then it's filled with different shapes. In this case, we had triangles, and over here it was rectangles, maybe squares, hard to tell from the perspective. So the notion is that we can take a figure and pack it densely along this bottom region and create a 3D space for a 3D volume for us. And I have a computer animation that does a fairly nice job on this. Guess it's not open. Let me see if I can, not that one, this one. So the Sketchpad example does a nice job of illustrating what we're after, and maybe you can get a notion of this 3D object that is created by cross-sectional pieces. So I'm going to drop the axis so that we can see our function on a flat surface. Before I go back, let's bring that back up. I'll just reset. There we go. There are two functions that form here. One of the functions would be y equals the square root of r squared minus x squared. And in this case, it looks like our r is set at 2. So it's a circle equation. And of course, we have an upper and a lower function here. Here would be my negative function representing the bottom part of our figure that we're viewing. So there are two functions here. We could think of this bottom one being f of x maybe, and the top one being g of x. We'll use those two functions as we go through notes. So we'll drop this axis and flatten out. And we're going to fill it with squares in the first case. So I'm going to just show you 4 squares. What you'll notice about these 4 squares is that as the distance between the upper and lower curve, f of x and g of x, changes, so do the squares, so do the dimensions of the squares. So my first one, you can see that there is a small triangle in front, or small square in front. And then as the distance gets longer across our two functions, then the square gets larger because its base becomes wider, therefore its height has to match that base since we're working with a square. Let's go ahead and sweep one of these squares. You'll notice it's growing. It hits the diameter right now, biggest square ever, and now our square is starting to shrink and become smaller as the distance between f of x and g of x gets smaller. At this point now, it's going to get smaller. If you want to see the solid that's created by densely packing many squares, imagine every one of these squares sitting side by side, and we get a nice 3D figure formed. It's kind of interesting, isn't it? We can show the solid without all that animation going on. Some pretty cool animations. Here's the square growing in size. There's your largest one, and now they're starting to shrink in size again. So the question of the day is, well, how much volume would this contain? We can do this also with equilateral triangles. I'm just going to show you those 4. This one is equilateral. Yeah, 3 sides are equal on them. And we can sweep that triangle. We also can create the solid. Very cool. So I'm just going to hit reset and then go back to our lesson. Let's see if we can get out of all this. All right, back to the lesson. Well, let's figure out how to calculate the volume. It says in this introduction, calculus cannot only be used to find volumes of solids created by revolving the 2-dimensional shapes around an axis, but we can also create volume of solids formed by cross sections that are geometric shapes. The principal ones we're going to work with are the 4 that are on your notes: squares, right isosceles triangles, equilateral triangles, and semicircles. Sometimes rectangles are also used, so I think I might squeeze that in at the end. So in this lesson, you'll derive the formulas for finding the volumes of the solids, given that their cross sections are squares, blah, blah, blah. The general form of the volume of a solid with known cross sections is volume equals the integral from a to b of a of x dx, where a of x is going to represent the area of the known cross section. You can see it right here, it's defined there. So what we really want to do is pick out one of the pieces and figure out the area for one piece, and then we can integrate. So we're going to find it kind of in generic terms of the area. So in front of us we have a square that would be one of these squares that was placed perpendicular to the surface that we are filling. Just a few notes. You can see that this is f of x, so I'm going to write f of x because it's my above function. G of x follows and becomes the lower function. This is the x-axis. We have the y-axis. Of course, this would be the origin where the two axes intersect. To get the distance across the square, well, it would be the same distance from F across to G. How would I represent that? Well, I'm going to write it as F of X minus G of X. That would give me the distance across the base figure that defined the region for us. Now, since this is a square, don't forget, then we have both sides equal. So that makes this dimension pretty easy to follow too. It is also f of x minus g of x. So how would I calculate the area of that particular square? Well, it's going to be area is equal to f of x minus g of x times f of x minus g of x, or we could say f of x minus g of x quantity squared. This is the area of a square, changing as the dimensions or the measurements of f of x and g of x change. So it's a varying area calculation. If we added all of these areas up, we would get the volume of the picture above. So our volume will be simply, you know what, I'm going to do the volume is nothing more than the area multiplied by the thickness of our figure. So up here we had that square, but this square does have a little bit of thickness to it. So I'm trying to draw just a little bit of thickness. So here is the square, and then the thickness is going to be dx for us because we are situating our figures perpendicular to the x-axis. Notice if I drew on down, I'd be residing perpendicular to the x-axis, which then gives me a little bit of thickness on my figure here of dx. All right, got that all established, so we can go forward. The volume will be the integral from a to b, the intersection of that base figure, and we'll go back and grab that so I can explain it. F of x minus g of x, quantity squared, multiplied by the thickness. The thickness is our dx, the area is this. And that is all that is to it to get the volume when using cross-sectional pieces. Let's label this intersection point here as x equals b, and let's label this one as an x equals a for the intersection. And that is why I integrated from a to b. Next, we're moving on to an isosceles right triangle. And we know what the word isosceles means. It means that two sides of the triangle are the same, and it will be the two legs since we're talking about a right triangle. So the two legs will be congruent. The hypotenuse, of course, will be longer. And in this picture, we're going to orientate ourselves such that the leg is positioned on the surface. So it's the distance across the leg that I'm interested in. Now, there are times that the AP will take this figure and position it so that it's the hypotenuse that is crossing the region. And that's a little bit different calculation. But for now, we're going to take the easier version and let's just do the legs. So, base figure is an isosceles right triangle, isn't it? I need to capture this distance across the base, which, oh boy, looks like our picture got turned on us a little bit. So I'm going to call this my g of x. I think that's what it says there. And then the upper function will be f of x going along the back side there. Let's say that they intersect again at x equals a, and this intersection point's x equals b. This would appear to be then our x-axis. We have our figures positioned perpendicular to the x-axis, and then this, of course, is our y-axis. Origin sitting down in here somewhere. All right, get ourselves oriented. Now, the distance across is going to be the difference. I guess black's not going to show up real well there. The distance from f of x to g of x. And you know how we talked about top minus bottom always being a good way to figure out distance between these? So once again, we're doing top minus bottom. When I go find the area of my triangle, I know the formula for a geometric shape that's a triangle would be 1/2 the base times the height. So what I need to do is calculate also the height of my isosceles right triangle. And that height, since it's isosceles, we know we have the two legs equal. It too is f of x minus g of x. So f of x minus g of x, let's bring this together then. The area formula is going to be 1/2 of the base, f of x minus g of x, multiplied by the height, which is also f of x minus g of x. And we get f of x minus g of x quantity squared multiplied by 1/2. Bringing that down a level then, we need to go into our volume formula because that's what we're trying to estimate or actually calculate. From a to b, these are x values where x equals a and x equals b. And it's going to be a 1/2. Well, let's just put our 1/2 out front since it's a multiplier. And then I'd have 1/2 of f of x minus g of x, quantity squared sitting in my integrand, and then multiplied by the thickness dx. So there's a lot of similarity between a square and a triangle. The only thing that is different is the fact that I ended up with a 1/2 out front. Now, I'm going to take you back up here. Let's compare. If I have an isosceles right triangle, isn't it just half of a square? It kind of makes sense that we see this half coming through, doesn't it? All right, next one, equilateral triangles. Let's get our picture set up here. This is, we've been doing bottom as g of x. Okay, let's do our bottom function as g of x. Our top function is f of x. This here would be your y-axis. This here would be your x-axis. Origin sitting here. Let's say it intersects at x equals a and x equals b. Notice the figure this time is an equilateral triangle. So since it's equilateral, all three sides are equal. It wouldn't matter which side it's oriented on, right? It's always going to be the same. What we'll want to do then is find the distance again across the curve. And of course, it gets its widest point, it looks like about in there. But it's still going to be a calculation of f of x, my top function, minus g of x, my bottom function. So I can capture that this base is f of x minus g of x in length. To calculate the area of a triangle, that's easy. It's 1/2 the base times the height. So I've got my base. What I need is the height of my equilateral triangle. So I tried to draw in an altitude or the height. how do I get the measurement for that? That's the tricky part, isn't it? Well, what we'll want to do is think about equilateral triangles. You know a very good property of equilateral triangles, and that is the fact that they have three congruent angles. Mainly, they're all 60 degrees each. And this top one, if I drop in a perpendicular segment, it bisects the angle up on top, so I get 30 degrees on each side. Where is this taking us? Well, it's taking us to a special right triangle that you studied in geometry, into a 30-60 special right triangle. Do you remember the characteristics of that? Well, the short leg was always x, and then we can move to our longer leg by multiplying by radical 3. I could also move to the hypotenuse from that short leg, and if I doubled it, let's write 2x, doubled it, that gave me the hypotenuse. So, while I'm looking at this thing, I see half this side represents a 30, 60, 90 right triangle. That means that my height is going to be this times root 3. Well, how long is my pink segment here? Well, the pink segment's going to be 1/2 of my base, f of x, minus g of x. 1/2 of that. That gets me this portion right here. I might as well write it down here as well. Minus g of x. F of x minus g of x times 1/2. That gives us the short segment. And if we multiply that by a root 3, we get the long segment. So now I want to multiply this by a root 3. So that ends up looking like root 3 over 2 times f of x minus g of x. And that is the height of a 30, 60, 90. All the things we get to learn today, or relearn. The area will equal 1/2 my base. The base is the, let's write base by this. The base is the long segment, isn't it? So I'm going to have f of x minus g of x multiplied by the height, which we had over here, root 3 over 2 f of x minus g of x. And that is the area of the triangle. Ooh, simplify before I go down below on calculating volume. We could bring our two multipliers together, so we'd get root 3 over 4. And then I notice I have f of x minus g of x quantity squared. Didn't we have quantity squared on those others? That's interesting. So volume is equal to root 3 over 4 integration from a to b. Remember, these are x values if we run perpendicular to our x-axis and our cross sections are sitting perpendicular. F of x minus g of x quantity squared multiplied by the thickness dx. Never want to forget that. All right. The semicircle, I'm going to go ahead and finish. I might have students coming in, but I'm going to just quick give you the rundown on this. Distance is f of x minus g of x again. The radius will be half of that, 1/2 of f of x minus g of x. And the area of a semicircle is going to be 1/2 the radius. Oh, I forgot pi in there. The radius squared, so pi radius squared. Which will turn out looking like 1/2 times pi times our radius, which is a 1/2 f of x minus g of x quantity squared. And that half is included in that quantity. So this turns into a let's just go pi over 2. 1/2 has to be squared. It becomes 1/4 f of x minus g of x. 1/4 times pi over 2 gives me pi over 8. That's what I was looking for. I forgot my squaring there. F of x minus g of x quantity squared. All right, so once you get the area of your cross section, then we can go into volume. I'm going to pull this forward and just call it pi over 8, and the integral of f of x minus g of x is squared dx running from A to B. And that is it. Now, the one thing that is in common to all of these, if you noticed, it was the distance across our base region, quantity squared. And we integrated from x equaling A to B. The only thing that changed was the number out front. So if you could memorize a few of these, you wouldn't have to sit there and rebuild them. Memorize that a semicircle is pi over 8. Memorize that an equilateral triangle is root 3 over 4. Memorize that an isosceles right triangle with one of the legs as the base area distance is a 1/2. Hey, cool. See you guys later. Ooh, talking homework though. Homework is the A through G, A through F, this. What it is, A through F. See ya.